Hi everyone, this is JF, or if you prefer, Professor, here today with you to discuss the sum of independent identical variables. As you know, most variables do not act like normal variables, but there are certain situations where they will start tending towards normal laws. This is what the video will be considering. As a first example, let's assume that X represents a Bernoulli experiment, so a one-trial experiment, with a probability of 1 over 6. Think, if you wish, of a die that you throw, and obtaining a 6 would be a success. Now clearly, this variable is not normally distributed. It has 83% chances of producing no successes, and 16.7% chances of producing one success. Every other outcome is impossible. But if you were to repeat this experiment 6 times, then the total number of successes that you'll observe has a new distribution. If you were to toss the die 18 times, the total number of successes also looks different than it did previously. If you were to repeat the experiment 36 times and add the total number of successes, now look at the distribution and how it seems to take the shape of a bell curve. The bell curve itself is centered around 6, which is not surprising since 36 trials with a 1 over 6 chance of a success is expected to be 6. Consider this other example where X represents a Poisson distribution with 1 as the average number of successes per time period. Once again, on its own, one Poisson distribution does not look like a normal distribution at all. Most outcomes are close to 0 with very, very few chances of having 6 or 7 or 8 or more appearances. However, if we were to add the number of successes over many time periods, for example, 2 time periods, the distribution takes on a different look. Every dot represents the total number of successes observed over 2 random experiments, in this case, 2 periods of time where successes are counted. Here are the total number of successes over 4 time periods, and over 8 of them. And once again, look at how the shape of the dots is starting to look normal. So what do these two examples have in common? Well, the variables that were considered had identical distributions. In the first case, we were repeating Bernoulli experiments. In the second, we were repeating Poisson distributions. The variables are independent. The toss of a die has no influence on the result of the next toss. And the variables were added to create a sum. It's actually the sum that started acting like a normal distribution, as long as we had a sufficient number of variables being added. So here's a fact that we'll be using quite frequently from now on. If x1, x2, xn represent variables that have the same probability distribution and that are independent, then the sum of these variables will converge to a normal law as long as n is big enough. More specifically, t will have a normal distribution whose average value will be the sum of the expected values of each of the variables being added. Since each variable is identical, we'll essentially have n times the same number. Because experiments that are independent allow you to add the variances, then the standard deviation is the sum of the variances of each of the trials taking place. So what is big enough? Well, in general, we use 30 as a guideline to determine if the sum consists of a sufficient number of identical variables. There are many examples where 30 will be insufficient, and sometimes 24 might be acceptable, or 16. For example, Independently of who is pitching, Johnny Baseball, a Major League Baseball player, gets on base, whether it be with a safe hit or a base on balls, with 36% probability. For all those who are not familiar with baseball, just think of every at-bat as being a trial, and every base hit or base on balls as being a success. If we let X represent the total number of at-bats, so the number of trials that will be needed to get to his next on base, so to obtain the next success, then what probability distribution does X truly obey? Well, we're counting trials until a first success is obtained, and that would mean we're talking about a geometric of probability 36%. Now, let's represent T as the total number of at-bats Johnny B will need to get his 100th on base. What distribution law does T obey? This time, we're discussing a negative binomial because trials will lead to a first success and then eventually to another, and we're counting total successes or total number of trials until 100 successes are finally attained. Okay, let's look at this differently though. The total number of at-bats Johnny B will need to get his 100th on base. What other way could we have represented the law to describe T? Well, 100 successes means that Johnny B will make trials or go to the bat until he gets a first hit. And then you could begin the new experiment until he finds a way to get a second hit. And then you start counting at-bats until a third hit is obtained. Every time the next hit or the next way that Johnny B will get on base is a geometric experiment. So essentially, the total number of at-bats is the sum of all the individual geometric experiments that lead to the next hit. So we are adding identical variables. We can assume they're independent because the number of at-bats needed to get the first hit should not influence the number of at-bats to get the second. And the sum consists of 100 such variables, which is bigger than 30. So, by the fact that we stated earlier, we could very well assume that T will act like a normal law. In this case, the average of the normal law will be the sum of the expected values of each geometric. So 100 repetitions of 1 over P. In the same manner, the sum of the variances caused by the independence of the variables is obtained to produce standard deviation. Suppose that yearly claims made by clients of an insurance company have an average value of 2,500 with 4,900 as their standard deviation. If X were to represent the claim of a randomly selected client, then the expected value of this variable would be 2,500, and its standard deviation would be 4,900. Fine. Nothing says X obeys a normal law, however. But if 36 clients were randomly selected with replacement to guarantee the independence of the results, and if T were defined as the total claims of the 36 randomly selected clients, then T, the sum of these individual claims being made, would have an expected value of $90,000. Here we're using properties of expected values for sums. The variance for the total claims would be the sum of the individual variances, since we are assuming independence. And from that we could get the standard deviation for T. Furthermore, because we are adding enough identical variables, and because we are considering them as being independent, and lastly, because we have at least 30 of these experiments taking place, then the fact we stated says that T should act like a normal law. And the expected value and the standard deviation for T now become the parameters that describe this normal distribution. We could then proceed to calculate probabilities for T, such as what's the probability that total claims will exceed 120,000? At this point, we use notions that we've learned before, which means, for instance, calculating probabilities in a leftward direction, and Excel can then be used to find a numerical answer. In this case, we would find that 15% is the probability that claims will exceed or be equal to $120,000. A variable x that obeys a binomial distribution could fit as a particular case. Binomials are sums of independent and identical Bernoulli variables. So we definitely have a sum of independent variables. X obeys a binomial with n trials, p probability of a success. And according to our facts, we will occasionally be allowed to replace x by a normal law. Notice how NP is the expected value of the binomial law and will become the average value for the normal. NP1 minus p is the variance of a binomial law, and rooting that number will provide the standard deviation for our normal law to represent or to estimate x. So approximating x by who is in fact a binomial law by a normal law is accurate enough as long as n is at least 30, as long as n times p and n times 1 minus p are both at least 10, and take note that to calculate probabilities for individual values, we will replace k by an interval, 1/2 to the left and 1/2 to the right of it, so that it is a 1-unit interval centered at k itself. Remember that normal laws have 0 probability for individual values. Independently of who's pitching, Johnny Baseball gets on base whether it be with a safe hit or a base on balls with 36% probability. If we were to let x represent the number of times Johnny B will get on base over a set of 100 at-bats, then x would be a binomial law where 100 trials take place, 36% chance of a success at every given trial. In this case, n is at least 30, n times p and n times 1 minus p are both at least 10, so it would be appropriate to replace this binomial law by a normal law. N times p and the root of np1 minus p will provide the average and the standard deviation for this normal law, 36 and 4.8. To find the probability that 36 hits will be obtained over 100 trials, obviously we could use the exact binomial law and get the right numerical answer, which is 8.3%. However, we could also use the normal law that estimates the binomial as long as we consider 36 successes as being the interval 35.5 to 36.5. And then the normal law's parameters and the use of Excel will give us a numerical answer for this estimation, which happens to be 8.3% as well. So note that replacing an individual value k by a 1-unit interval centered around that number is typical of any situation where a normal law is used to replace a discrete random variable. In example number 3, for instance, we could have replaced the negative binomial with 100 successes to achieve by a normal law because the negative binomial consisted of 100 identical geometric experiments. If we were to use the negative binomial to calculate, for instance, the probability of obtaining or of having 290 trials before getting the 100th success, 1.47% would be the answer. If we use the normal law with the parameters that are the expected value and standard deviation of the negative binomial's distribution, we would observe the exact same conclusion.